Everyone, we are going to discuss about some mathematical analysis related to transient condition of DC motor drives. Here we will find current versus time relationship, torque versus time relationship, so that we can understand that how much time the motor will take to overcome the transient condition. Already in last class we have discussed that transient conditions are nothing but starting, braking, plugging, reversing, or change in any parameter of the a circuit to generate some kind of disturbance in the electrical system. So, how much time the drive will take to overcome this transient condition, we will discuss about these things. So, let's start. So, before starting the transient condition or transient analysis of DC machines, let's again see the block diagram of the drive system. So, here nothing but it is a source. Same block diagram is applicable for DC as well as AC drives. So for DC drives, this is DC source, power electronic converter, DC motor, load, sensing unit, control unit. Now, now the sensing unit will sense current, torque, or speed from this motor or motor load system. Then the sensed value will be processed through a control unit based on the reference parameter or desired output. And this control unit will generate switching pulses for this power electronics converter. So ultimately, this closed loop system function is to control the on period or the switching pulses of this converter. Now the transient condition may be because of any fault in this power electronic circuits or across these motor windings or in these circuits also. So in designing a complete electrical drive system, knowledge of this transient time, that means how much time it will take to overcome this abnormal condition. Starting, braking, reversing, speed changing, and load changing are the transient operations which generally occur in industrial drives. In designing an electrical drive system, following informations are very important. How current, torque, and speed of the drive motor changes with time in transient conditions. If we are going for suppose starting, then how much time the drive system will take to reach the speed from 0 to desired speed, or current from 0 to operating current. Similarly, torque. Then what are the kind of losses takes place in the drive system and time taken for completion of this transient process. So before discussing those things, here is a comparison between rotational and linear system. In rotational system, though it becomes important here to discuss a little bit about this rotational and linear parameters. In rotational system, generally we are saying angular displacement. In linear system, it is linear displacement. Then angular velocity, it is rate of change of angular displacement. Here it is rate of change of linear displacement. Then acceleration, rate of change of angular velocity d omega dt. Here acceleration dv dt. Then polar moment of inertia j, it is equivalent to mass in linear system. Torque is equal to polar moment of inertia into acceleration. Here force is equal to mass into linear acceleration. So torque and force are analogous to each other. M, angular momentum. Here it is J into omega. Here it is M into V. Then kinetic energy half J omega square. Here it is half M velocity square. Power torque omega. Here force into velocity. Work torque into theta. Theta means angular displacement. Then work is equal to here force into linear displacement. Now let's start the modeling of this complete system to find the current versus time as well as torque versus time characteristics, or you can say the relationship between current versus time and torque versus time. So we have to go through various differential equations and we have to solve based on the initial parameters to find the unknown values. So here, before discussing those things, it is important here to discuss this again. This is a separately excited DC motor. Ra is the resistance of the armature winding, La inductance of the armature winding, Ia is the armature current, and this is the back EMF developed across the armature conductor, it is motor constant phi omega. This is the field excitation. Vf is the supply voltage for this field winding, Rf resistance of the field winding, Lf inductance of the field winding, and If is the current. Now this flux phi can be controlled by controlling this If as well as the speed. Suppose this motor is connected to a load. So motor load system, then the motor load system can be represented as a common polar moment of inertia, that is G. B is coefficient of viscous friction, and when it is multiplied with omega m, that will give viscous torque that is to be supplied by this motor along with this load torque. So T is equal to TL plus B omega m. That will be the equilibrium condition. These fundamental equations again we will discuss. Let's discuss about this DC series motor. Likewise, here it is supply voltage for this armature, then armature resistance, inductance of the armature, armature current. This is the field winding of DC series motor. It is K into phi, depend upon the armature current. E K phi omega m, and this phi can be represented as Kf into Ia. We have seen that. Same load is connected to this motor. J polar moment of inertia, or the equivalent polar moment of inertia. B coefficient of viscous friction. This is the load torque required and to be supplied by this motor. To obtain mathematical equations related to this one, let's first define these things. V is your source voltage, I is the armature current, E back EMF, B coefficient of viscous friction in Newton meter per radian per second. J polar moment of inertia in kg meter square of the motor load system, referred to the motor shaft. Voltage equation of the armature circuit under transient condition can be obtained as V is equal to RAIA plus LA DIA dt plus KE phi omega m. So this, in the steady state condition, this LA DIA dt it will be 0. If the current is constant, IA is constant, then this term will be 0. But at the time of transient condition, this current will not be constant. So it will change. That's why this is voltage equation or the KVL equation at transient condition. Now from the dynamics of the motor load system, as I told you, J d omega m dt is equal to T minus TL minus B omega m. So this term viscous frictional torque I have not considered, but it is to be supplied and it is directly proportional to the speed of the motor. If speed is very high, then this B omega m cannot be ignored. Further, torque is equal to K phi Ia. So the above transient equations are valid for all types of DC motors. Just you have to represent this flux in separately excited motor, it is constant, or shunt motor, you have to consider this one as constant. So point number 2, for separately excited DC motor, flux remaining constant, equation 1 and 2 are linear differential equations. So here phi is constant, then this one and this one becomes a linear equation. So it is easy to solve these linear equations compared to non-linear equations. And when it will be non-linear, in case of series motor it will be non-linear, because Ia is not directly proportional to phi because of saturation of the magnetic field. Or within saturation or in the linear region, if you are operating, then also it is linear equations. Flux is a non-linear function of the armature current, and therefore equation 1 and 2 are non-linear in case of DC series motor. Now in separately excited motor, we are going to consider when field current is constant, flux remains constant. So K phi we can consider as K. So very simple equations it will become. So equation 1 and 2 becomes V is equal to RAIA plus LA DIA dt, and this term becomes K phi is equal to K omega. Then J d omega m dt is equal to KIA minus TL minus B omega. So this is nothing but T, or the torque developed by the motor. You can see here T is equal to K phi Ia. Now K phi already we have considered K, so KIA. So that's why this expression becomes J d omega m dt is equal to KIA minus TL minus B omega. Differentiating 4 with respect to time. K dia dt is equal to J d to omega m dt square plus b d omega m dt plus dtl dt. Now from equation number 3, just take the value of this dia dt and substitute in equation number 5. You will get this one. And arrange the equations, you will get this equation number 6. So tau a d2 omega m dt square plus 1 plus tau a by tau m1 d omega m dt plus 1 by tau m2 omega m kb jra minus 1 by j tl plus tau a dtl dt. Now here this tau a and tau m1, it is tau a is equal to la by ra. This is armature circuit time constant. L by r, we know that the time constant of the circuit. Now this tau m1 is represented as j by b and tau m2 is equal to jra by bra plus k square, just to reduce the complexity of this equation. Now differentiate equation number 3. We will get k d omega m dt is equal to dv dt minus ra di dt minus la d2ia dt square. Substituting in 4 from d omega m dt from 7. Here you just take the value of d omega m dt and substitute in equation number 4. And rearrange the equation, you will get tau a d2ia dt square plus 1 plus tau a by tau m1 dia dt plus 1 by tau m2 ia is equal to 1 by ra tau m1 b plus tau m1 b dv dt plus k tl by b. So these equation number 6 and 8 we have to solve. So from this equation number 8 you will get the value of ia in terms of time. Obviously you should know the initial conditions to solve this equation number 6 and 8. From this equation number 6 you will get torque versus time relationship. That means from equation number 6 you can find how much time the system will take to achieve steady state in case of a starting condition, or 0 in case of braking conditions, or different transient conditions you can obtain based on the initial conditions. And the transients you are going to analyze for this separately excited DC motor system. So today we have discussed about transient analysis of separately excited motor. We have modeled the complete drive system based on KVL equations and found out that linear differential equations can be solved to find current and torque of the system, and from there we can obtain the time required to die out these transient conditions during starting, braking, plugging, etc. Thank you.